We're ready to start. We continue today our discussion of congestion control in the internet. We will continue this first part where we will explore the fundamental mechanisms and why they are this way, in particular additive increase, multiplicative decrease. But before that, we need to continue exploring what fairness means. We have seen that the goal of congestion control is to allocate the rates in an implicit or explicit form such that the allocation is Pareto efficient, which would avoid congestion collapse. But there are also multiple ways of being Pareto efficient, and we would like some way that is fair. Unfortunately, there are two definitions of fairness. One is max-min fairness, which is very extreme in one sense, and another one, which is perhaps more reasonable, is proportional fairness. We have seen that proportional fair and max-min fair allocations always exist, at least in the context of networking, and are unique, so this is a concept that we can really use. This is where we were, and let us look how one can concretely compute in this small example the proportionally fair allocation. I'm showing here a toy network with a number of links and one red flow that uses all the links and a number of blue flows that use only one of the local links. We have seen that we can interpret proportionally fair allocation as the job of maximizing a global utility function, the utility of the network. That's a concept that is used by some theories of economy where a socially optimal economic situation occurs when the different agents are maximizing some utility, some social utility. Here the social utility is the log of the rates. We have seen that this is equivalent to the axiomatic definition of proportional fair allocation. So here we have to maximize the sum of those five logs subject to four constraints that express the capacity limitations here. The function here to maximize is concave, and the constraints are linear. Therefore, the set of constraints gives a convex set. And maximizing a concave function over a convex set is a convex optimization problem. The other type of convex optimization problem being to minimize a convex function, maximize a concave or minimize a convex function. Concave means that the returns are diminishing. The utility, if we increase from a large amount, the delta to the utility is itself decreasing. For a function of one variable, concavity means the derivative is decreasing. The second derivative is negative. So we could ask MATLAB or whatever other tool to solve that exactly, but in our case, we know also that the optimal must be Pareto efficient. If it's Pareto efficient, that means that there must be some constraints, perhaps not all, there must be some constraints that are satisfying. In this specific case, it must be all constraints because all the constraints have independent free variables that allow them to be maximized. For example, the constraints on the first link can be maximized by maximizing x1. If I have a value of x0, x1 that does not satisfy the constraint with equality, I can always increase x1 because x1 is not involved in other equalities. It's an independent variable compared to the other constraints. So we must have equality here and also everywhere. In general cases, that would not happen. In general, you have combination of constraints, and there may be some constraints that are not satisfied with equality. For example, if all flows would be using all links, and one of the links would have a much higher capacity than the others, then only the bottleneck links must be satisfied with equality at the optimum. Here, it means that we can reduce the problem which is in dimension 5 to a problem with a unique variable, x. I call x star the optimal value of x0 here. And at the optimum, we must have that x1 plus x0 is equal to c. And the same in all, so that gives this constraints here. Right. So at the end, what we have to maximize is a function of x star only. If I take the sum of all the logs of the rate, that gives log of x star plus 4 times the log of the others, of each of the others. So I have now a function of one variable. It's high school mathematics. You have to maximize a function of one variable. You study the derivative. We see that the derivative is decreasing. And if it cancels, if the derivative becomes zeros in the interval, it must be the maximum. If it does not, then the maximum must be at one of the edges, at 0 or c here. Here, we can cancel the derivative, and after some math, we find that the optimum is c over 5. 5 being the number of variables, which is here the number of links plus 1. So the optimal, we find, is to give 1 over 5 to the red flow and 4 over 5 to the other blue flows. This is what the proportionally fair allocation will do. We can observe that it satisfies the goals, which were to account for the use of resources in some way. Here we see that the red uses 4 links, the blue only 1, and in this specific case, it turns out that that's exactly the ratio between the allocations. Compared to the max-min fair allocation, what would be the max-min fair allocation for this one? Well, the max-min fair allocation is very simple to obtain. We do water filling. We increase all the rates until we hit the bottleneck. Those that have hit the bottleneck, they stay there, and then we continue increasing the other rates. Here, if we increase all the rates, the red and the blue, until we hit one bottleneck, we hit all the bottlenecks together and add the value, which is the same for the blue and the red, which must be, therefore, C over 2, 1/2 of C. So 50% of the capacity. This is what the max-min fair allocation would give. It would give the same to the blue and the red, and completely fair, the same to everyone, which is just half of the capacity. Proportionally fair allocation will not do that. It will give less to the red because the red is using more links. A little guessing exercise. Here is another scenario, one we have seen before, where we had studied the max-min fair and Pareto efficient allocations. Which one is the proportionally fair allocation? The correct answer is D here. So you can do the complete math, or you can use some qualitative reasoning. Well, A is the max-min fair allocation. And if you have some memory of what we did last week, we saw that this one is not proportionally fair. By looking at the axioms of proportional fairness, we could increase it. There was a delta that was possible to do to this allocation, such that the average rate of change was positive. So we could improve it in the sense of proportional fairness. So this one is not the proportionally fair allocation. Now if we look at B, B is not Pareto efficient because of this value here, x1 plus x0, this here, is less than this capacity. And since x1 is a free variable, I could increase x1 to reach 10 megabit per second. So I can do better unilaterally here, which means that this allocation is not Pareto efficient. It's not maximally efficient, without speaking of fairness. Since we know that the proportionally fair allocation is always Pareto efficient, this cannot be the proportionally fair allocation. Now we can use some heuristic reasoning to see how the proportionally fair allocation differs from the max-min fair allocation. In many scenarios, they are the same. If the constraints are decoupled in particular, they can be the same. But if they differ, they would tend to give, proportional fair allocation will tend to give less to the flows that use more resources here. Here it's the blue flow. So C and D are both deviations from A. You can check that they are both Pareto efficient. They're hitting all the limits that can be hit. C is giving more to the red compared to the max-min fair at the expense of number 1 and number 2 here. And D is doing the opposite. D is giving less to the red to the benefit of the blue and the green. So we expect D to be the proportional fair allocation because that's what we expect to happen. Of course, this is not a very reassuring answer, so we can do the math. very similar to what we did before. We can analyze manually to see which of the constraints must be satisfied. Again, I stress that this is sometimes easy in simple cases. In generic cases, it's a very hard thing to do. Which constraints must be satisfied? And very often, many constraints are not satisfied with equality. But here again, because the blue and the green decouple the constraints, we must have equality here. Then I have to maximize this function. With a bit of high school math, we see that it's for optimal value of 10 over 11. So that is the story of proportional fairness. Proportional fairness is perhaps, in some sense, the more reasonable thing we would like to achieve for a congestion control mechanism. We will see that for a variety of reasons, TCP does this almost, but not exactly. What TCP does is something that has received a name, which is called utility fairness. Proportional fairness is maximizing a function of the rate, which is the log. So the function is the same for all sources and is equal to the log. If we do that in general, in economy, it has a name, it's called the utility fairness. So there are simplistic theories of economy that assumes that all economical agents are maximizing their utility. And their utility is how much benefit you receive from buying something or from selling something, minus how much it costs you to acquire that thing. For example, if you buy a new smartphone, the penalty you have is the price. If it's very expensive, you don't like it. But if it's very fancy, you can give a high positive value to it, and you do the plus the value you get of your fancy smartphone minus the price you pay. That's your utility. That's the simplistic vision that some economy theories can use. And so here we can see that proportional fairness is simply using the log here. Now, other functions have been used, and in particular, it's interesting to see that if you use another function like this one here, which is a not very exciting function, but it's 1 minus 1 over x over m, where m is a positive number. And if m is very large, you will have a function that starts looking like an impulse. It's minus infinity in 0. Then as soon as x is not very small, it's very close to 1. And in between, of course, it is a smooth function here. If we let m go to infinity, and if we compute for every value of m what is the utility allocation that we obtain, then we find that when m is very large, in the limit, what we obtain is the max-min fair allocation. So the max-min fair allocation can be thought of as being approximately a utility fairness, where the utility function is practically the same regardless of the rate, and is minus infinity if you have 0 rate. Approximately, because if you take such a function and you try to maximize it, what you maximize is not the max-min fairness. Because if you give 1 to whatever rate, it doesn't matter which rate you have. So it's not exactly true. Max-min fairness cannot be expressed as the solution of a maximization problem. We have to express it as the solution of the water filling algorithm, which is a sequence of optimization problem, not a single optimization problem. But intellectually, in particular, when we will try to reason about what really happens in the internet, it's useful to remember this fact. Proportional max-min fairness is like proportional fairness in some sense, but with a utility function that is more skewed, that is less smooth. I mean, log is a very beautiful function. It's a nice curvature that increases smoothly. If you take something that looks more like an impulse function, which is more irregular, if you want, that has a larger second derivative in this corner here, then this gives max-min fairness, which corresponds also intuitively to what we said before, that max-min fairness insists on giving the same to everyone, whereas the proportional fairness will have a more steady increase here. So what did we see so far? Well, we saw that congestion control has to implement some form of Pareto efficient allocation of rates, and ideally it should be perhaps proportional fairness. Right? Now the question is how we do this concretely. Now, in networks, there is a number of mechanisms that are used, have been deployed, and to some extent are still deployed today. Some of them are competing. In a large fraction of networks, in particular today in MPLS networks, we use what is called explicit rate-based. So you have a central controller or a distributed controller that gives explicit instructions to the source, saying, you source, the rate at which you should send is this one. Of course, if you have such a simplistic view of the network, it's very simple to make sure there is no congestion collapse and also some form of efficiency. Perhaps it's difficult to be exactly Pareto efficient, but it's easy to be relatively efficient. But of course, the drawback is who calculates the rates and why and how. It's okay in small network. This is typically done in something we will discuss a bit next week when we do class-based queuing, where for some reason you want to give a certain rate to some applications. For example, in an industrial environment where you have sensors that are sensing data and send them to actuators. For example, in an Airbus, you have a number of devices that sense and send the information to a central calculator that decides how to navigate and orientate the flaps, for example. So those streaming applications have to have a guaranteed rate. You don't want to allocate to them a rate that is given by proportional fairness. They need exactly the rate that they need. If they send one message every second, for example, and if the message is 10,000 bytes, they need 10,000 bytes per second. Not less. If they give less, if you give less, some of the messages can be lost. If you give more, there's no benefit for those applications. So this is typically used in controlled environments, industrial environments. I mentioned MPLS, which is a kind of industrial IP, if we want. Also in cellular networks, if you buy a Swisscom subscription, the only difference you will have for different prices is the rate. You can have a very small or a very large, and you pay much less for the very small than for the very large. What does Swisscom do? When you connect to a base station, it does an explicit rate control on you. So you are receiving a rate which is not proportionally fair. It's the rate between you and the competing resources for the spectrum. Like in Wi-Fi. In Wi-Fi, if we all in this room use a Wi-Fi, we compete with each other. Wi-Fi provides a form of fairness, which is close to proportional fairness. But Swisscom will not do that in cellular network. It is a controlled environment where it is proportionally fair between all the people who have the same class of service. So you can manipulate those things, and 4G and 5G systems have mechanisms to explicitly give a rate by how many chunks of frequency and time slots you give to different devices. You get more or less rate. This is not the end-to-end rate, though. This is the rate that you get between you and the Swisscom network. If you access YouTube over that, if the YouTube server is congested, you may get less than the rate that is allocated to you by Swisscom. Or if the path between Swisscom and the YouTube server is congested because it goes through other internet service providers, then you may get less. So those are what can be done with explicit rate base. Intellectually, it is much simpler than what is done by TCP because you have a system that can explicitly allocate rates based on user subscriptions. In other devices, for example, in some gigabit LAN switches, also in some distributed application systems, some other simplistic mechanisms that are called stop-and-go signals. Imagine you are an Ethernet switch and one output port is congested. One thing you can do is you can send back to all the other switches to which you're connected a signal that is saying, reduce the rate at which you're sending. This is called a back pressure signal. Some devices do it in this way. Some others send a stop signal. They send stop, and when you receive a stop signal, that means you stop for a few seconds, not forever, and that will that will reduce the problem for this switch. Of course, it's like saying when you go to visit an office that has to do some work for you, they say, no, stop, don't come in. But then what you're doing is, in fact, pushing the congestion upstream. And if you push the congestion upstream, and if the network is a ring, then you push the congestion everywhere, and at the end you might have deadlock and inefficiencies. So back pressure is used in very simplistic scenarios. In complex network, in meshed networks that are not trees, this has problems. So you need to complement it with other mechanisms to avoid deadlocks and inefficiencies. I mentioned rate control. Rate control is done in the cellular network per class of service. And inside one class, as I mentioned, it provides some form that is similar, that is close to what we do with internet, which is using fair queuing per flow. We'll talk about that a bit later when we talk about class-based queuing. And then what is the basis of today's best effort internet? Best effort means that the rate I receive when I connect to the internet is not decided by the subscription I pay, but is decided by the current state of the network. The network will do its best effort to give me as much as it can, but there is no guarantee, there is no number tagged to what I obtain. This is what is the status today of the internet. Some people hope that in 5G and 6G networks we will have perhaps more controlled environments where we could have higher rates for some applications than others, but today this is not available other than in industrial private networks, but not in the global internet. This is based on end-to-end congestion control. And the principle of end-to-end congestion control is that hosts try to estimate what is happening in the network. Does it look congested? Does it feel congested? If it feels congested, they will send less. If it feels okay, they will send more. So they are, in some sense, good citizens. We have seen that if a network is congested and you send as much as you can, so if you are selfish, even if you are the only one doing that, it's good for you. But if everybody does that, we have seen that this may lead to congestion collapse, inefficiencies for everybody. So what is dictated today in the internet is that we should have the hosts send what is possible. And the major algorithm that is used is very simple. It was invented in the 80s. It was published in 87, but it was in operation, in fact, before on DECnet. It's called additive increase, multiplicative decrease. So what we will do now is see what is the justification for this system here. And this is also the one that is done in TCP. It is based on those very simple analyses. I assume that I am the network and sources are performing congestion control end-to-end. That means that sources send traffic and then they get some feedback from the network to see what is the state of congestion of the network. In the DECnet idea, that is the one that we still find today, the feedback is binary. It's a single bit. It's called today ECN, Explicit Congestion Notification. We will discuss that in a few minutes. It is simply saying, is there congestion or not for this packet? So every packet that goes through the network sees whether the queues look full or they don't look full. If they look full, it will mark there is congestion. And if we're using TCP, there is an acknowledgement flow, so we can return this information back to the source. So the source gets, at every time t, a feedback, which consists in one bit, and this feedback is 0 or 1. So to analyze this mathematically, we will assume that the feedback is obtained in this very simplistic form. If the capacity is not exceeded, no negative feedback. If the capacity is exceeded, so if the sum of the rate exceeds the capacity of the network, then we send negative feedback. Again, this is a simplistic model. It's assuming the network is made of a single link, or a single bottleneck link, if you want. We will see what happens when we have more than one link, what happens to such a scheme here. And then the feedback must be incorporated to do tasting the water, as we discussed before. So if a source receives a negative feedback, it will reduce its rate. If it receives a positive feedback, it will increase its rate. That's the principle of the one-bit feedback. And then if you have to make a control law, the first thing you will try probably is a linear control law. So this is what Raj Jain, the author of this additive increase multiplicative decrease system, did. So he examined all the possible linear control laws. So the control laws consist in saying my rate before receiving the feedback was this one. I have to compute the new rate here, and the new rate must depend on the previous rate and also on the feedback I've received. So if I've received a feedback 1, a negative feedback, I will do a linear function of the previous rate, and similarly, if the feedback is positive, 0, no feedback, no congestion feedback, but of course with different values of the coefficient. Now, obviously, we want to decrease when we do that. So if we want to decrease, that means the multiplicative factor here must be a decreasing factor. So it must be a number less than 1, or in the worst case, equal to 1. And the additive part here also should be negative, or in the worst case, 0, because we want to decrease. And vice versa for the increase part. So if we use a linear control, we have 4 possible actions. 2 when we receive negative feedback. We can decrease multiplicatively, we can decrease additively, and of course we can combine the 2, and 2 similar actions when we receive positive feedback. Here is an example of such a control law over a small simulation that is a simple link that has 3 sources here. And here I'm showing as a function of time the rate of source 1, of source 2, and source 3. You see that source 3 started its operation after sources 1 and 2 at time 100. And what we see is that this scheme, of course, has oscillations because we always increase or decrease. We see also that source 1 started at a small value, source 2 started at a large value. And if we ignore the oscillations, we see that they are oscillating around the same value. So in average, source 1 and source 2 get the same value here. And we see also that when source 3 comes in, that results in a reduction for source 1 and 2, and source 3 also stabilizes to a value which is the same. And here this is showing what is the total capacity. We see that we exceeded, the capacity was 10 in this toy example, and the total capacity is sometimes a bit more. This is necessary for receiving negative feedback. This is the simplistic model and how it can be explained here. Now, we want to achieve the thing that is given, that is shown here, but you will not achieve it for all values of the parameters. So let's analyze qualitatively what can happen, right? We would like to be efficient, and we see that this scheme is efficient in the sense that we always increase until we receive negative feedback. So probably we will fill the links. We will be forced to hit the capacity. However, we would also like to have some form of fairness. Now, in this very simple example, in this toy analytical example, it's easy to reason about fairness because in this case, max, min, fair, or proportionally fair allocations are the same. If you have a single bottleneck link, if you have n sources that each have no other constraints than the fact that they share their bottleneck link, then all max, min, or proportionally fair allocations will give the same result. They will give C over n to each of the sources. It's easy to see. For max, min fairness, by increasing by the water filling algorithm, we'll see everybody will have C over n. For proportional fairness, we can reason by saying, well, we're maximizing a utility function. The utility function is the same for all sources. The constraints are the same for all sources, so the problem is completely symmetric. So at the optimal, the solution also should be symmetric, so it's the same for all. So the theory of fairness here is simplistic. We'll come back to it and see later. But still, we need to make sure that this dynamic adaptation algorithm reaches a fair allocation. To reason about it, let me plot here the case of 2 sources, x1 and x2. Of course, we need to do it for more than 2, but it's harder to plot. For 3, we could, but for 4, more difficult. Here I'm plotting the evolution of the algorithm. So if I start at a given rate, so x1, x2 are the rates of sources 1 and 2, and this blue line here is the capacity, is the condition x1 plus x2 equals c. So we should be below this line here. And the goal of a congestion control algorithm is to bring the point close to this line. It is at this line that we will be Pareto efficient. So any allocation that is on this line, because here I have a single constraint, the Pareto efficient allocations are the ones that are at this boundary here. Now the fair allocation, because the thing is completely symmetric, are the ones that give the same rate to both. x1 equal x2 gives me this diagonal line here, and there is here only one Pareto allocation that is fair, whatever fairness criterion you take, and this is the one that gives the same to all. So the red circle here is the target. Now this algorithm is iterative and oscillates. It's not something that gives one value. It gets there by multiple steps. So I'm showing several steps here. Assume, for example, I receive no feedback, so I increase x1 and x2, so I do this move. Then I receive no feedback because in my simplistic model are below capacity, so I continue to move. Then here I receive a feedback, so therefore I will move down here. And the question is, by doing that, will I get to this point or will I get somewhere else? To analyze what happens, let's understand what it means here to do multiplicative decrease and additive increase. Here I'm proposing two moves. One move is doing only additive increase and multiplicative, is doing additive increase and multiplicative, and the other one is doing multiplicative increase, we're doing only increase. So the additive increase means the multiplicative term is equal to 1, and the additive increase means the additive increase means the multiplicative term is equal to 1, and vice versa. The multiplicative increase means the additive term is equal to 0. Right? So we do only a multiplication by a coefficient that's larger than 1, or here we do only an addition by a number that's positive. So if we would do if we would do additive increase, that means whenever we receive positive feedback, we add something to the two components. Which one is which? And the correct answer is A, because what? Well, because of elementary geometry. If I add a constant v0 to the two coordinates, then what am I adding to this point is a vector that has two coordinates equal, so it's parallel to the diagonal. Right? If I multiply each of the coordinates of x by a constant number, then I'm staying on the same line here. So if we do additive increase, we are blue. If we do multiplicative increase, we are green. Right? Now what happens if we do, so let me stay here. What happens if we do this, if we would do only multiplicative increase, for example? Remember, the goal is to get to the red point that is in that corner. So if we start from a place here, when we do multiplicative increase, we keep the ratio of the different allocations the same, which means we're not improving fairness. One measure of fairness, in this simplistic case, fairness is everybody has the same. So how would you measure whether a vector here is very fair or not? How would you measure this? Is this x very fair, or is another x that I'm drawing here fairer? Well, one solution would be the angle between the diagonal and this vector here. Or in other words, the inner product with x and the vector that has all components equal to 1 divided by the norm of x, which is the cosine of this angle. This is called sometimes the fairness index. We see that when we do a blue move, we get the angle reduces. If we do a green move, we don't. So that's for the increased term. So when we increase blue, we get closer to fairness. When we increase green, we don't change the fair or unfair situation. Now, same situation, we can increase, but when we receive negative feedback, we will also decrease. If we can do the same reasoning. If we do multiplicative decrease, We don't make fairness better or worse. We stay at the same angle. But if we do additive decrease, we make fairness worse because we move here in this parallel line. So it's obvious graphically here that the angle increases if we do that. Well, that's the analysis that was done in the 80s and is still the basis for what we have today in the internet. What does it tell us? Well, if you do such a linear control mechanisms, you should not do the red move. Because if you oscillate here and if you do red moves, it's a bad idea if you want to go to this target here. You can do the green, but no, if you do only the green and the yellow, you would have a rate, you would have an evolution of the system that will eventually reach the Pareto efficiency line, which is here, but you will never reach the red point. You will not get to a fair point. The only move that brings you to a fair point is in fact the blue one here. So you must do additive increase. You can also combine additive increase with multiplicative increase, but if you want to move as fast as possible towards fairness, you should do additive increase. Now about the decrease, you should not do additive decrease. So in summary, you should do blue, perhaps some green, but it's not very efficient, and certainly not red. This is why in the internet we do multiplicative decrease, additive increase. Among all the linear controls, of course, you could imagine more sophisticated nonlinear controls, but those are the ones that, roughly speaking, are what is done in the internet, right? So now let's come back to the more general problem. Assume I have a number of sources. Now in a network situation, assume one of the network we saw in the previous quizzes, and assume the sources don't get a rate, which is given from an oracle that says do this or do that, but they apply this adaptive algorithm to move their rate by sensing congestion on the different links until they reach an equilibrium or they oscillate around an equilibrium. If we do that in a general setting, what do we obtain? We have seen that if we do that in a simple setting with a single bottleneck link, then probably we will get to the red point. In other words, we will get to the max min or proportionally fair allocation. In general, what do you think we will obtain? And the majority, which is very egalitarian, hopes that we obtain max min fairness. Well, if you think about it, if we would do that, I would not have taken the pain to explain proportional fairness. The reality is a bit more complicated. Here is the solution. If we do exactly additive increase, multiplicative decrease with the same parameters for everyone, the same u and v are the same for everyone, we will obtain a form of utility fairness where the utility function is this thing here. This can be obtained by analyzing this as a dynamical system. It's not an exact analysis, but we make a fluid approximation where we replace the changes that are discrete by something that are infinitely small steps, and then we can approximate this system, which is stochastic and has steps, by a fluid system that is given by ordinary differential equation. And if we study this system, we find that solving this ordinary differential equation is the same as maximizing this. You have all the details of the analysis in the lecture notes that are available on Moodle. We will not go through that. It's a bit long and not so exciting in the context of what we're doing now. But this tells us, in fact, if we look at the utility function that this obtains, it is, I compared the utility function. Now it's always risky to compare utility functions. To compare them, I force them to have the same value at this here. So it's a rescaled version of the utility function. If everybody in a network is maximizing a given utility function, if you add the constant to the utility function, or if you multiply the utility function by the same number from everyone, you will have the same allocation because everybody has the same proportionality factor or constant added to it. So I did that here. I rescaled the proportional fairness, so the log and the blue function here, such that they are the same at a value of 10, and this is what we obtain here. So we see that this function is in fact deviating from proportional fairness in the sense that it's more going towards a step function, which intuitively means that this is not far from proportional fairness. It's a utility fairness, so it's a good system, but it's probably closer to max-min fairness. It's in between max-min fair and proportional fair allocation. Since we don't know anyhow which of the two is good, being between the two is okay. In practice, of course, computing this allocation will require solving an optimization problem, which we don't do in reality. We let TCP do the job automatically for us. That's the first thing we will see. So this AIMD is the basic that is implemented in the internet congestion control of TCP. After the break, we will see that there is another mechanism called slow start, which is very easy to understand, but is causing a lot of confusion in literature or in user manuals about congestion control. And we will discuss that after the break.